Hello, everyone. This is week 3. So, this week is all about how atoms stick together, the chemical bonds that form every substance around us. We have two main types of bonds. We're going to start with first our ionic bonds. So, the definition of what ionic bonds is a bond that is formed by the electrostatic attraction between opposite charge ions. Think of it like magnets with a positive and a negative. And these ions, which is atoms with a charge, they attract each other. And this bond that comes from their attraction is going to be called ionic bond. So the process is one atom, usually a metal. So usually a metal completely transfers its valence outermost electrons to a nonmetal. And from this, they form an ionic bond, where the metal, because it gave up its electrons to the nonmetal, becomes positive, and then the being called a cation, and then the nonmetal receiving those electrons from the metal becomes even more negative, becoming an anion. So why do they do this? So every atom wants to achieve the stability of a filled outermost shell. So by the metal atoms usually when they give up their electrons, they fulfill their octet rule because their valence shell just kind of like disappears, and they end up with like their innermost shell is now octet, while the non-metal usually once it takes those electrons from the metal, it is now fulfilling its octet rule. All right. So now that's all you have to know for ionic bonds. So now we're going to cover covalent bonds. So a covalent bond is a chemical bond formed when two atoms share pairs of electrons. So in here, the only difference is going to be there's no transfers. So you have something like hydrogen and another hydrogen. And this one has one electron, and this one has one electron. So they just come together and they share their two electrons, forming a single bond. And this is going to be covalent. They both hold, like if you look at them, they both hold two electrons because they're both sharing those two electrons. And the players in this situation is going to be two nonmetals. It's always going to be two nonmetals. And just like ionic, the goal is always to achieve a filled outermost shell. That's the reason why they do this, which increases stability. The next topic is going to be Lewis structure. So Lewis structure are drawn out forms of electronic configuration, which we talked about last week. So it's a diagram that helps us represent the bonding between atoms in a molecule and shows the electrons that are not like particularly shared. And these electrons that aren't shared are going to be called lone pairs, and they're going to be these things right over here. So two dots that are just alone, not shared by the other electrons, are going to be lone pairs. And then lines, these lines that you see over here, that represents shared electrons. So an example of this like drawn is going to be something like if somebody told you Draw the Lewis structure of nitrogen. Let's ignore this. Let's just act like we didn't see this. And they told us draw the Lewis structure of N2. So in order to draw it, you will first start by asking yourself, how many valence electrons does nitrogen have? So if you look at a periodic table, I'm going to search up a periodic table with you guys. This way you guys can see it as well. Periodic table. And if you look at nitrogen, and you look at like the group number, if you look at the group number 1, 2, all the way to 15, 17, 18, this last number right over here, this 5, tells us how many valence electrons this entire group has. So nitrogen has 5, phosphorus has 5, arsenic has 5, Sb has 5, Bi has 5, etc. But nitrogen, we know it has 5 valence electrons. And then it also tells us that we have ×2 nitrogen. So then we basically write both nitrogens with 5 valence electrons, 1, 2, 1, 2. But you might start doing it like this, like with the lone pairs, like just doing lone pairs. But what you have to know is when it comes to nitrogen, all these things, they always follow a rule, or basically they have to have one each and then they start pairing up. So it'll go like this and then they start pairing up over here. So this equals 1, 2, 3, 4, 5. And then we also have over here, so it's going to be 1, 2, so filling every single thing with 1 and then pairing them up. So as we can see over here, these two nitrogens aren't fulfilling their octet rule. So they have to share in order to fulfill their octet rule. So if we share one of them, now they have a total, now this nitrogen, let's see if they fulfill their octet rule. So it'll be 1, 2, 3, 4, 5, 6. So it's not fulfilling the octet rule for that one. So we're going to go ahead and do another bond using those 2 electrons that I just erased. So now they're sharing 4 electrons in total. Let's see how many, like if they're fulfilling their valence electron, like their octet rule. Yeah. So it'll be 1, 2, 3, 4, 5, 6, 7. Because if you see a line, it'll be 2 electrons. So it's only 7. They're still not fulfilling their octet rule, which is always going to be 8. So we're going to go ahead and do another pairing. And now we're going to count to see if they're fulfilling their octet rule. So we have these 2 lone pairs, 1, 2, 1, 2, and then 2, 3, 4, 5, 6, 7, 8. So now they're fulfilling their octet rule, and this is going to be the entire Lewis structure for just these nitrogen. And then you continue doing this for each one. All right, so the next thing that we're going to learn about is going to be the types of bonds and bond lengths. So when atoms share electrons, they can share different amounts, which affects the strength and length of bonds. So what this means is going to be a single bond. Like we have 3 different types of bonds that we're going to learn about in chemistry: a single bond, a double bond, and a triple bond. A single bond has 2 pairs of electrons. It'll be like this. It is going to be the longest, and it is also going to be the lowest energy, and it's going to be the easiest to break. A double bond, which shares 4 electrons in total, looking like this, will be medium length, and it will have medium energy, which makes it stronger than a single bond, but it's going to be weaker than a triple bond. Which brings us to triple bonds, which is going to have 6 pairs of electrons showing up as 3 lines. So this is going to be the shortest. It's like kind of like sewing. So as you add more lines and more like threads, it comes closer and closer, and they become also stronger. So you can't like really tear them apart so easily. And this is going to be the hardest to break. So if you want, I'm gonna just go ahead and write this down. So single bond is going to be longest, weakest, double bond, medium. It's going to be medium in strength and length, and triple bond is going to be the shortest and strongest. So this should help you with your homework for week 3. Which week 3 and week 2, we're combining the homework. This way you guys aren't like doing 2 different homeworks, and it's easier to turn those work in. Now we're going to cover resonance. So resonance is basically just the movement of electrons. So when we draw a Lewis structure, like as you practice Lewis structures, you're going to realize there's like many different ways and more than one correct way to place double or triple bonds. So they're often drawn as resonance structure is going to be drawn. So I think it's better if I show you a resonance structure. So it's basically just the movement of electrons. So they're basically moving this, the double bonds, or a triple bond, and it's also going to be moving lone pairs as well. So these are just going to be switching positions. So if we look at this example right over here, and we're trying to show the resonance structure, these two are going to be resonance structures of each other. And usually how you draw like the final form is you're just going to draw like a hybrid of them. And that we're probably going to cover in week 4. But so in order to show how this resonance structure like turned into this, you can just basically like this came over here. So this bond, this single bond broke and formed a lone pair over here. So a lone pair is now forming over here. And then for this one, for this one over here, we have this lone pair coming over here to form this double bond, which results in this structure. And then for this one, the opposite happens. This bond breaks, forms these lone pairs. And then for this one, these lone pairs form this double bond. And these are resonance structures of each other. It just shows the movement of electrons. But they are literally like the same molecule. They're both like O3. But it just shows the different movement of electrons. And then the next thing that we're going to talk about is something called VSEPR configurations. So this is determined, so how atoms bond, and so after atoms bond with like what we learned about, like resonance structure, ionic bonds, covalent bonds, double, triple bonds, they have like a certain shape. And this shape is going to be determined by the VSEPR theory. So this theory states that every region of electrons density, whether it's a bond or a lone pair, will spread out in 3-dimensional space to maximize the distance between them. They push away from each other as much as possible to minimize repulsion. So basically, VSP theory maximizes the space around any region of electron density, bonds, or lone pairs. So to make it easy, all you have to know is they differ in angles, and they differ, the reason why they differ is going to be because of the number of groups. And groups can be classified as either lone pairs, or they can also be classified as just like an atom around it. And this we're going to I'm going to show you right over here. So starting with linear, if you look at this linear one, right, we have this atom, and it's surrounded by X, and it's surrounded by X. So it's surrounded by two different groups, or two of the same groups. It can both be hydrogens, but it's surrounded by two groups. So because it's surrounded by two groups, it is going to, like, these two groups don't want to be around each other. So group number one, group number two do not want to be close to each other. They don't like each other. So they're going to be like far away from each other on opposite sides of the room. They do not want to be with each other. So this is going to cause for their structure to be like linear. So they're going to be all the way on opposite sides of the room, no matter what. If this one were to come, like if number two were to come over here or something like that, number one will be like, you know what, move away from me. So number one will literally go right over here. And then at the end of the day, it's going to be linear. So number two is we're going to look at trigonoplanar. So we have a atom right over here, and it's surrounded by three different groups. So it's surrounded by 1, 2, 3. And these X's, if I haven't mentioned yet, are going to be atoms. So it's surrounded by three different atoms. And all these atoms don't want to be close to each other either. They don't like each other. They don't want to be associated with each other. So they're just like, you know what, keep your maximum distance away from everybody. So they're going to be 120 degrees apart. If you do like, if you look up on a calculator and you do 360 divided by 3, you get 120 degrees. So this, like, from this entire, like, think about it as like a circle, from this entire circle, for them to be like perfectly separated from one another is going to be 120 degrees. That's why these atoms form a 120 degree angle bond away from each other. And this is going to be named as trigonoplanar each time they do this. So like I said, atoms represented by X are not the only things that are going to be seen as groups, or the number of groups surrounding an atom. Lone pairs as well can be seen as the number of groups surrounding an atom. And when lone pairs are like surrounding an atom, you're still going to consider it like three groups surrounding one atom. So it's going to be like trigonoplanar, but not exactly. It's going to be bent or angular, just because it's not exactly 120 degrees apart. It's going to be a little less than 120 degrees apart, just because these lone pairs, they're not that, like, they still don't want to be around other atoms, but they're not that bad. So they can get a little bit, just slightly, a little bit closer. And then the same thing can be seen in tetrahedral. So you first look at the, like, if we follow this, we're looking at the number of groups. 1, 2, 3, 4. So automatically you think tetrahedral. And then you continue doing it for each one of these. The main ones that you want to memorize is going to be 1, 2, 3, 4, 5. All of the rest, like, you don't really see them a lot when it comes to chemistry. Okay. So the next thing that we're going to learn about is going to be polarity. And this is like going to be the second to last slide. We have like one more to go. So we know that VSEPR tells us the shape. We're now going to look at polarity. So polarity refers to the uneven distribution of electrical charges within a molecule. It happens when a bond has different, like when two atoms in a bond have different electronegativities, which we discussed a little bit in the periodic table during week 2. The atoms with the higher electronegativity pulls the shared electrons closer to itself, making the side of the molecule slightly negative and the other side slightly positive. This creates a dipole moment. which is a moment of separation of charges where you have like one side being negative and then the other side being positive. So basically, like to show you this, an example is going to be like something like chlorine and chlorine. So electronegativity is how much an atom wants to fulfill their octet rule or wants electrons, right? So if we look at chlorine, it's going to be a halogen. Halogens are going to be group 17. They're always going to have 7 electrons in their outermost shell on a like regular day. And you have them here over here. And since they're the same atom, we automatically know, you know what, these atoms both want one more electron really badly. And they're both nonmetals, so they're going to share their electrons. So when they come close to each other and everything like that, these atoms, chlorine, are going to be kind of like this. And if you look at it from an outsider's perspective, they both equally share that these 2 electrons to form their octet rule. So it'll be 1, 2, 3, 4, 5, 6, 7, 8. So they both equally share it. So if you look at this, this is going to be a non-polar molecule. But like I'm actually going to mention something about intermolecular forces right now because I feel like it's a good time to mention it. So they're going to be, in the outsider perspective, they're going to be non-polar. There's not going to be any charge. But as these electrons are moving around and everything like that, they're moving. At some point, one of these some of these electrons are going to be focused on one side. They're going to be focused on one side more than the other. And then the other side is not going to have enough electrons. And then they're going to focus on another side as they just move around the atoms, basically. Move around. This is going to cause for like partial positive and partial negative charges. But overall, because these 2 chlorines are going to be like the same molecule and they both want these want the electrons, and the electrons continue moving around them, this is going like it's still going to be non-polar because they're still sharing these electrons, and not one side is going to be like basically dominating the other. They're both going to be like equally dominating, trying to get these electrons. And that is going to be called London dispersion forces, where partial charges that increase with surface area are created from transition differences in electron density from electron cloud. So you basically have electron cloud, and these electron clouds basically like move around. Sometimes they center around here more, which causes for this one to be negative and this one to be positive. And then sometimes you have the opposite effect, and then this is negative and this is going to be positive. And it just continues going on like that. And this like basically this iffy positive negative that continues to change and everything like that, which is overall non-polar, like we discussed, is going to be called London dispersion forces. Okay, so now we covered London dispersion forces and we covered polarity. I'm also going to show you another example of polarity just to like bring like the entire, just to put a bow on polarity basically. It's going to be chlorine and hydrogen. So chlorine, and we have hydrogen. Hydrogen has 1 electron. Chlorine, halogen always has 7 valence electrons around it. So chlorine is really close to fulfilling its octet rule and everything like that. So it really has a high electronegativity. While hydrogen, on the other hand, hydrogen is like always giving up its stuff. So because of this, you have chlorine being highly negative, basically almost pulling all the electrons from hydrogen, while hydrogen is going to be partially negative, partially positive. And this is going to be like a polar molecule, because of chlorine basically being like bullying hydrogen to take its electrons. So if that's not clear, just let me know and I'll also clarify that. And this is going to be called a dipole attraction. Like if we had two of these, like two negative side, and then we also have another one, like hydrogen positive and chlorine negative. When these two polar molecules come together, they form something called a dipole attraction, which is an attraction between partially charges on carbon to more electronegative atoms such as oxygen, nitrogen, halogen. So it's basically this. Okay, now we're going to, so I'm just going to cover some of the physical properties that comes with polarity. So polarity affects solubility, how easily something dissolves in a substance like water. And it affects boiling point and melting point, as well as we discussed, like kind of the intermolecular forces. So polar molecules are going to be more soluble than nonpolar molecules because water is a polar substance, right? And if you have this attraction basically between these positive negative forces, they're like exchanging between one another. Sometimes these bond breaks, which causes for it to dissolve like. So you have polar interacting with one another, the molecules dissolve and things like water. So they're going to have a higher solubility than non-polar molecules, which wouldn't really interact with a polar substance like water. And then polar molecules stick together better. So polar molecules, they like to interact with one another. They're just like best friends. They're like, always sticking around with each other. So they take more energy to like break apart, which is what happens when something boils or melts. So it's harder for them to boil or melt as well. So basically, polar is more dissolvable, and it's also going to have a higher boiling and melting point, and its intermolecular forces are going to be stronger. So I'm gonna give you another overview real quick of intermolecular forces, and then we're done with this with week 3. So ion dipole strongest is the strongest ion dipole is going to be the strongest intermolecular forces. It's the attraction of fully charged ions and a polar molecule like water. So if we have something like H2O, so we have oxygen, HH. So let's use VSP real quick to just like name this. So we have 1, 2, 3 groups around it, but one with a lone pair. This is going to be bent. And if you want to, like, if you know why it's called bent, then you're good to go. Like, what we're doing for like the next homework and everything like that. But it's going to be basically an ion dipole attraction is going to be this, and something like sodium that just gave up its electrons. Like this attraction between them is going to be the strongest. And then we have hydrogen bonding, which is going to be hydrogen with fluorine, which is fluorine, oxygen, and nitrogen. So if you see hydrogen bonded to fluorine, oxygen, or nitrogen, that's going to be a hydrogen bond. It's going to be the second strongest intermolecular force. And then we have van der Waals forces, dipole, attraction between partial charges on carbon to more electronegative atoms such as oxygen, nitrogen, and halogens. So this is the attraction between two simple polar molecules. Like this explanation I feel like makes it complicated, but it's basically the attraction between two polar molecules. So a slightly negative and a slightly positive. So something like this is going to be dipole-dipole. And then lastly, London dispersion. It's going to be basically this. It's always in a molecule. No matter if a molecule is polar or non-polar, the electrons are always moving around it, so it's going to always have that London dispersion forces. And that's basically all you have to know. Let me know if you guys have any questions. And yep, that concludes our video. Thank you guys.